I'm now going to hand over to Nick Heaton, a distinguished engineer from Cadence Design System. Nick works in Cadence Systems and Verification Group as a distinguished engineer responsible for Interconnect, Workbench, and a number of other ARM-related solutions. So I'm going to hand over to Nick now, seamlessly.
Thanks very much, Mike. Great to be here again. Great to see so many faces. What I thought I would try and give you is maybe a vision of what we're seeing as the problems and what's going to happen in the next 3 years. But I wanted to take this opportunity really to go back to the first one of these events, which was in November 2011, to see what we said were the challenges and what was the vision 3 years ago, just to see, you know, I think it's a great opportunity because we've now got 3 years of history of did we do what we said we were going to do maybe. And this is some of the very brief flip through some of the slides that was presented by Mike Stelfox, who's a Cadence fellow, 3 years ago. So we were predicting and seeing in the market an explosion of SoC challenges. There's still new IP being built and verified or whatever, but a lot of the devices we were seeing 3 years ago are large collections of IPs, hundreds of IPs. And I think that trend has definitely continued. If you just look at the progress in 3 years on ARM IP, as an example, bigger, substantial systems are now coming out into the market. And software, obviously, is a key piece of that, and I'll mention that again. But from an IP perspective, that SOC challenge presents a need to make sure IP in its own right is more robust. You don't want to be finding bugs as you integrate these massive systems, right? So there's both if you like, a top-end challenge, but also there's more of a responsibility on the designers to, if you like, design right by construction. And make the IP integration ready, as it were. So most IP these days has a software aspect. So when I started designing a long time ago, I could do the whole chip myself. The first chip I did was entirely me. There was no processor. It's just hardware design. Way beyond that point, we need some software aspect in the IP. So thinking about how IP gets integrated and the flows you need to make that SOC integration more efficient was something we were concerned about. Furthermore, in integration of the SoC, automation, I think, is something, certainly we had a vision 3 years ago that automation would become an essential part of that. I think it's very interesting, again, going back to ARM, but their acquisition of Dualog is very interesting because this is an IP integration automation tool, if you like. So there's definite moves in automation, and we focus mainly on a more contained problem, if you like, in our first instance, which is interconnects, but I'll talk about that later. But certainly, what are the common themes across SoCs that you can look to and automate? If you're going to turn these designs around every year, or whatever the ping rate is for your particular market, if it's mobile phones, it's, you know, every year. Maybe not the same for all of you, but you need to be able to predictably integrate these designs, and that's a massive challenge. Looking back on ourselves in terms of EDA 3 years ago, we had very distinct platforms. There was TLM platforms, there's RTL simulation platforms, emulation platforms, FPGA platforms, and actually for most of the people building SoCs, they needed all of them, and actually in each of those buckets there's a big challenge, and the test bench requirements and whatever were different, and trying to make that more efficient, I guess, was one of the visions we had. And again, software is becoming such a massive part. Whether it's actually part of the delivered product is not the issue here. It's the amount of software you have to build that potentially you throw away. You deliver the SoC, but you build a ton of software to actually validate it. That problem has got much worse in 3 years, I would say. And the scale and the amount of software content that SoC developers are having to construct is daunting. It almost dwarfs the verification team, the software team, for just the bare metal that gets thrown away. So that's a big cost in the development of the SoC, and addressing some of that was our vision 3 years ago. Okay. So what's happened in the 3 years? Okay, what have we done, or what's the market done, I guess, in terms of delivering on some of those or all of those challenges? Well, the first thing is, in terms of the individual platforms, so if you take, in terms of Cadence's offerings, there's 6 core engines. There's TLM, there's formal, simulation, emulation, FPGA, the whole range of platforms. Bringing those together and making them seamless to use, I apologise to the mental people who are using the word seamless, if you can move between those abstractions more easily. And what do we mean by move between them? You want consistent debug, right? You want to know that the debugger you love and use in the TLM domain is the same debugger you use in the simulation domain, in the emulation domain, right? You want to know that low power, is supported across all of those platforms. That wasn't the case 3 years ago, right? There was a whole war going on, and that's all kind of been resolved in terms of IEEE resolution, but actually making that happen has been pretty tortuous, but we've got there. The platforms themselves have moved on, and when I talk about what's coming in the next 3 years, I can't go into all of these solutions, right? It's a very complex space. I'm going to pick out a few things to talk about. But the management of all the data that's generated, that's a big, big challenge. This is not just coverage anymore. It's not just functional coverage, right? There's all sorts of other things that everyone's been asked to measure. It's kind of the era of big data is upon us in terms of verification. VIP needs to be usable across all of these platforms. I would say today that's still not a completed project, but we've moved a long way forward. A lot of the VIPs run on emulation, FPGA prototyping, and there is commonality evolving in that space. It's still a very fast-moving space. Software. So I'm going to talk a little bit more about some of these things in a little bit more detail, but software and the ability to start to automate the creation of software for bare metal testing. We're not talking about application software here, we're talking about software you need to validate that your SoC at least can move data across all of the engines, getting data from your application processor to your GPU, to your baseband subsystem. All of that data movement, even just basic data movement, is a massive amount of software. And addressing that is something we're going to talk about in a minute. So we've moved on a long way. In 3 years, things have improved dramatically. This is a very complex space, as I'm sure all of you are aware. And the number of solutions that you need to go from concept to silicon is kind of mind-boggling. The number of languages you need to be able to support. So anything can be done in terms of automation, consistency, and productivity is going to have a big benefit. And those are the kind of things we've been doing over across what we call the system development suite. Talking about the management of data. So, as I said earlier, when I did the first chip I designed, did everything. I did the design, the verification, the tape out, the test vectors, everything. But just verification is now a huge team effort. It's not one or two guys in even in the same cube. they're geographically distributed. You need to know and manage what's going on across all of the IP development and verification, the integration, investigations into power management, what's the bug rate. As I said, it's a big data problem. And this is not getting a smaller problem. It's not a problem that's shrinking. So being able to manage a true client-server database for verification is key. You need to be able to capture now software metrics. How much of my software have I covered? How much of my hardware have I covered? What formal checks have I done? What power domain tests have I done? Have I ticked that box? One of the aspects I've been doing a lot of work on in the last 3 years is performance metrics. How do you know, A, what your system, how your system is going to perform? And this gets more difficult with the model we've just described. If you imagine integrating lots of IP, is all of that IP under your control? It's highly likely that that's not the case, right? So you're buying in IP from a number of IP providers, you're assembling it. How do you know it's going to perform? So that's the first thing. And how do you understand how it's going to perform? In the last 3 years, cache coherency has gone from kind of, it was just about to come out in terms of ARM's first ACE spec, 2012. Well, it's become much more mainstream now. We have tons of customers doing ACE developments. Cache coherency is complicated, and you can't validate it at a single isolated block level. It's a system level concern in the same way that reset power clocks are system level concerns. And so you need to manage that kind of data. How do you set performance measurements and ensure when that last design change goes in, you tape out, it's still going to perform? You need a systematic way for performance validation that you've got for functional verification. If you think about cache as a classic example, if a cache isn't working, functional verification won't find out that it's not working, right? All cache does is improve the performance of the system. From a functional point of view, there's no difference. And that's key, that you have a performance aspect. And what you'll see, I think, is when I start talking about the vision, is that there are other aspects coming into this. Going back to the, and I've stolen, I said, I don't think Brian's here yet, I've stolen one of Brian's slides from a year or two ago here. The move, as I said, to make new IP robust before it's integrated, Formal has a massive part to play in that. And Formal has changed in the 3 years since that, when we first were here. Formal has kind of moved very significantly out of niche area into the mainstream. And it's key that the designers, it's easy for the designers to adopt this. So what you've seen in terms of Formal is that there's the concept of apps, targeted Formal apps for power, clock domains, unreachables. There's a whole raft of specific apps you run, and the designer can start to get confidence in a pretty automated way that the IP is of a certain standard. It doesn't mean it's fully integration tested, but it can be. What we're trying to do here is minimize the amount of bugs that slip through into integration, because that's really painful, finding those. Okay. And obviously, thinking about the next 3 years, there's a whole load more apps that you can start to think of that are going to be rolling out. Another aspect of another challenge, if you like, that we identified 3 years ago was the problem of fast software bring-up when you don't necessarily have all of the models available in TLM. TLM is a classic way of doing early analysis, early software bring-up. However, there's a dilemma here. If you haven't got models, particularly of third-party IP, so do you have a model of your GPU or your baseband or whatever readily available? Probably not. Well, how do I bring up my software early in that environment? Well, a lot of your IP is available in RTL, right? If it's third-party IP, it's available in RTL. What you can do is build a partial TLM system with the models you have available and layer it with the RTL and connect the two things together. So you get the benefit of a TLM platform. In this case, we're showing it using ARM fast models, but it can be any processor models. It doesn't have to be ARM. But the benefit here is ARM fast models run at potentially hundreds of megahertz. You can actually do OS bring up in very short order, Android bring up in minutes, and then test a new device driver with the real RTL if you haven't got a model. So this works in simulation, but obviously it's got real benefits in when you combine it with an emulator. So you can bring up your software, and we've got public endorsements list. For example, NVIDIA is a classic case. They don't have C models of their GPUs that they can use readily. They bring up Android, Linux, Windows, and actually test new RTL with those with the full stack. Now that gives you the kind of performance you need to achieve software levels of debug. The software guys like it because they use the regular ARM debugger, but you're actually using real RTL. So this is a combined, we call it hybrid. Furthermore, in software, and this is probably the most recent thing, this sort of chronological, these slides. The most recent thing we've announced is a tool called Perspecsister Verifier, which is really addressing the automation of creating software use cases. It can be used for UVM as well, but the predominant use model is creating software use cases. So what kind of thing do we want to do? Well, maybe I want to create a coherency test for my system. This requires lots of active agents, whether they're processors or coherent I/O, like a GPU or a PCI Express device, all trying to interact and use the coherency and checking that coherency is still enforced. Creating those tests is really hard manually, like incredibly hard, and you may write one or two tests. If you can automate the creation of those tests with a goals-driven approach, you suddenly get hundreds of tests. And you can kind of think of this as like constrained random for use cases. Okay, and this has a lot of benefits in other areas that I'll talk about in a minute. The first benefit is it's C. If we generate C tests, it will run in TLM, it will run in RTL, it will run in, maybe slowly in RTL, but it will run in RTL, it will run on Palladium, it will run on FPGA, it will run on post-silicon. So you've suddenly got all of the platforms, you've got the same use cases running. That's very powerful because now you can create tests early and they flow all the way through to post-silicon and bring up. But also you can target use cases for things like power management. Power management is a very complex system-level, system-wide problem, and you want to be confident that all of the power management you've put in doesn't negatively affect the outcome, your functionality. So again, creating software-driven power management use cases is really important. So that's a kind of very quick snapshot of some of the things we've talked about. Some of them we've delivered on. There's a whole load more detail, but I haven't got time to go into that. Where do we think? What do we think? What are we hearing from the customers? So, what are customers telling us are their big challenges for the next 3 years? And there's a number of them. I've picked out two specific areas. So verification, when I sort of started working with Specman in 2000, it was simulation, constrained random, hardware verification, function, that was it, right? Things have changed quite drastically. That was a long time ago, but quite drastically in terms of what's very interesting is that I go and see people talking about performance analysis, particularly that's my favorite topic. And actually it's the verification guys who are doing it, which surprised me. I kind of thought it would be architects and designers. No, it's the verification guys. And why is it the verification guys? Because you have to do it accurately at RTL. You can do stuff at TLM, but the granularity and the accuracy at TLM is like milliseconds. If you want to know whether something's going to deliver bandwidth, then you want to measure it at RTL, because that's what models most accurately your silicon behavior. And the same's true of power. The verification guys are getting dumped on this problem, and so the verification guys are coming to us and saying, how do we do power analysis? How do we do performance analysis? If you think about, and I don't work for ARM, so I've mentioned ARM a few times, but one of ARM's classic ways they define a core is PPA, power performance area. Well, what about the chip? That's actually the thing you care about most for the whole chip, not just the processor core. You want to know what power I'm going to need per megahertz per gate, if you like. And that's a really complex problem. And you've got three sort of aspects of this. You've got power performance and thermal, because there's a package it's got to go in that's got to get rid of this heat, right? And you need a whole load of analysis to help you do this. You need to be able to create performance use cases to do the performance analysis. You need to create power use cases to measure that accurately. And then you need tools to help you then decide if that power can operate within the package. Okay? Now we see this tight integration of those aspects really as where we're hearing this from a number of customers, that thermal budgets now are kind of dominating rather than area budgets, right? Used to be for a whole 20 years, it's can we squeeze a few gates out of this design to get it into a commercially viable silicon. That's still important, but if it busts the power budget, if it busts the thermal budget or doesn't perform, that's even worse, right? The second challenge we see is, and certainly in Europe this is very strong, is the change in automotive. Automotive, you think of it as some ECU inside your car engine. Well, actually there's now infotainment systems, a lot of safety aspects in terms of advanced driver assists. Well, this creates two big challenges. Generally, these are mixed signal devices, but they also have to comply to safety requirements that are way beyond anything in mobile that anyone's ever cared about. Will a track on the die wear out after 10 years? Right? How do you measure that? So functional safety is very key. So in terms of the first challenge, we already have a lot of the pieces in place in the system development suite in terms of verification. We have power management, performance analysis, but the integration of that with early power estimation and package thermal aspects is key. It's got to be easy for the guys building and doing this early to ensure they don't hit a problem way down the road. We also have done something in terms of functional safety, and there's going to be more coming on that. This is a very recent announcement, but you'll hear the 26262 number rolled out a lot more in the next few years, and we think that's a critical thing that's going to become, certainly say in Europe with a lot of automotive electronics, is going to become one of the key things. And so just to summarize, what I've done here is kind of give you my view of where we are and how things are moving forward. We had what we call the Stone Age of verification, directed testing, Verilog, whatever, for a number of years, and the constrained random came into being late 90s and is still going strong. UVM's come a long way and there's still refinements to that going to be coming out. But metric driven, where you start to take consideration of power performance, safety, mixed signal aspects, bug rates, all of that is still expanding, and that software is becoming a major part of that. Thank you very much for listening.
Thanks, Nick. Yeah,